Hello, everyone. So, last time we talked about how it was possible to determine the electron configurations or term symbols for a given atomic species. So, today we're going to try and figure out which one of those term symbols is the lowest in energy. So, to do that, we're going to invoke the full set of Hund's rules. And people have so far mostly talked about the simple set. We're extending this all the way. So, what we've done so far is we've now figured out which electron arrangements are possible. Now, I want to try and figure out which one is the lowest. So, to do this, we're going to work through an example set of our silicon electron configuration, with which its 2p electrons generates a possible 5 different term symbols or 5 different states, ranging from a singlet D to a singlet D with a singlet S with 3 triplet P's in between. So, in order to figure out which one of these species is going to be the lowest in energy, we have to invoke Hund's rules, which will rate the energy of our species using the spin, orbital, and total angular momentum. And because I have 3 properties to rate, guess what? We have 3 different rules. Each one will rate a different property, and they are listed in order from which one dominates the energy choice to which one will be tiebreakers. So our first and most important rule is more or less a restating of what we've seen before. If I've got a given configuration, so in this case, 2 electrons in a p orbital, not 3, the term with the greatest multiplicity will be the one that lies the lowest in energy. So this is more or less a familiar maxim in that we want to try and maximize our total spin, as this minimizes electron-electron repulsion due to spin pairing. Or in a rephrasing, if I have electrons with the same spin, they tend to stay out of each other's way, and thus I'll have less, they'll hate each other a little bit less. So of my previous 5 states, 2 were singlet, 3 were triplet. So our lowest energy states are going to be our triplet P states with J values ranging from 2 to 0. So again, these triplet states will be much lower in energy than the singlet state due to spin pairing energies, and this difference can often be quite substantial. But now I have to figure out which one of these 3 is going to be the lowest in energy. So for that, I can start by moving to the second of Hund's rules. So this one's a little bit less straightforward. But the idea is, for a given multiplicity, the term with the highest value of L will tend to have the highest energy, or lowest energy. So one way of thinking about this is that electrons want to occupy distant orbitals. If the electrons are right on top of each other, this means they're getting each other's way. So if I'm looking at the p subshell, for example, and I encourage you to go back to the structure of these orbitals, it turns out that the m sub l plus and minus 1 orbitals occupy exactly the same space. This also holds for the d orbitals with the plus and minus 2 orbital. So if I was going to if I wasn't going to maximize L, I might occupy put 1 electron in each one of these orbitals. And if I do that, they're sitting right on top of each other. And again, this leads to a lot of electron-electron repulsion. So again, let's think about my silicon system. I've got 2p electrons. And since I know that no orbital will want to be doubly occupied, I'm going to want to put 1 electron in the +1 state and 1 in the 0 state, where they stay away from each other. And when I do this, that gives me a net orbital angular momentum of 1. And again, this will hold if I apply the idea to a set of d orbitals, where I'd maximize at a value of 3, then 2, then 1, and the worst case is where everybody's paired up and I have an L of 0. So this will again support our choice of our p orbitals because again, despite the fact that the second Hund's rule would say that D would be the lowest, first set says that triplet will be optimized. But if I was going to figure out who is lower in energy in between my singlet D and my singlet S, I would tend to choose the singlet D because it has a higher value of L. So turns out in this case, the second of Hund's rules wasn't that helpful. So let's move on to the third. So this is our final rule. And this states that for atoms with less than a half-filled shell, the lowest J value will have the lowest energy. If I have more than a half-filled subshell, then the highest J will have the lowest energy. Now you'll note it says nothing about what happens for a half-filled shell. The reason why is that for a half-filled shell, I'll have equal amounts of electrons orbital angular momenta pointed up and down, so they should cancel out, and I'll have an L value of 0. And in this case, due to Russell-Saunders, J equals S. So there is no choice at all for my J value. Now, what this rule essentially is talking about is going to be spin-orbit coupling. And it turns out that if you have a half-filled shell, you can maximize the stabilization of spin-orbit coupling by minimizing J. And this is what we talked about before. But it turns out, due to some intricacies of electron arrangement, if you have mostly full subshell, you're going to be able to maximize your stabilization of spin-orbit coupling by having the highest J. It gets a little bit technical, but for now, just take this on my word. So what this means for our current case of silicon is that we're going to tend to predict our triplet p state to have a J value of 0. Because with only 2 electrons, I haven't yet half-filled my p orbitals. And so the J equals 0 is going to be predicted to be the lowest in energy. So putting these rules along with how we determine term symbols during the last lecture together, we can find a full method that will help guarantee that we find the correct correct and lowest energy term symbol for any atom. However, if I'm just remaining in the lower periods, say periods 1 to 4, where Russell-Saunders holds pretty well, we do have a shortcut we can use, and most of you will probably like this because it tends to be very visual. What we can do is take a simple electron diagram. In this case, let's walk through the p orbitals. So, again, as a reminder, the m sub L value on the left will be negative, and on the right will be positive. And I'm going to fill up my subshells left to right, 1 electron at a time. So, first up, let's walk through the second period, is boron. So in this case, I have a single electron pointing up, so I have an m sub s of +1/2. But I also have an m sub L of -1. So this gives me a doublet p state, and I have a negative L and a positive m sub s, so they cancel out, and I end up with a net J value of 1/2. Now, I want to let you know that this is a method that does correctly predict the correct term symbol, but this should not be taken as the correct electron configuration. One way of thinking about it is that this state is exactly the same as if I was to put a single electron pointing down in the m sub L +1 orbital, or, in all honesty, the 0 state. Any orbital will be the same for the angular momenta as long as the direction is opposed to my spin. So, just want to make you aware that while this is a method that correctly produces the right term symbol, this should not be taken as solemn word for what the actual electron configuration looks like. It's just one satisfactory condition. So with that said, let's go ahead and throw in a second electron, and this gives me carbon. I go ahead and I fill up, and now I have a net or total m sub L of -1 and an m sub S of 1. So this gives me an L value of 1, or a P, and a triplet state. So I have a triplet P, +1 on the spin, -1 on the orbit. They'll cancel out, giving me a J equals 0. Now, this is actually exactly what we want to see, because guess what? Carbon and silicon have the exact same electron configuration, because I don't care about the shell in this case. So carbon and silicon should indeed have the same term symbol, and this method does generate that. So we can go ahead and extend this guy to adding in a third electron and generating nitrogen. When we do this, we have an L value of 0, because -1, 0, +1. Everybody cancels out. I have an L of 0. I have an S state. And with 3 unpaired electrons, this gives me a quartet spin, or an S of 3 halves. And because when L equals 0, J has to equal S, I also have a J of 3 halves. So far, so good. Now we can keep on filling, except for now adding an electron pointed down. And when I do this, I'll generate oxygen. Now, it's worth noting, in this case, I have a L value of +1, or sorry, I have an L value of -1 and an S value of +1 from the triplet. So this gives me a triplet P state. Now, one of the things you should note is that because of our rules, we tend to it will tend to be that these guys will add together to give you a J of 2. Some people, in order to convey this, like throwing the third electron in the +1 orbital to emphasize that the directions should be additive. So we have a triplet P with a J of 2 for oxygen. We can extend this idea for fluorine, where I'll have a doublet state, and again, I'll have a J of -1 for the extra electron that's pointed out here. So again, this is on top of the L equals 1 from the nitrogen. So again, because we're more than half filled, these two orbital angular momenta will add together, and I'll have a J of 3 halves. 1/2 + 1. And again, feel free to put an electron in the last orbital if you want to. So this brings us to our last state, neon. This guy is easy. All of my spins cancel, and so do all of my orbital angular momenta. So I'm left with a singlet S state with no angular momenta. And you can feel free to walk through this idea for pretty much everything through the fourth period of the periodic table. After that, you have to watch out for JJ couplings, which gets a little bit messy, so I won't get into it too much. But when you pair this all together, what you can find is that it's fairly easy to determine the ground state term symbols of each and every element. And again, this holds fairly well through the fourth period. By the time you hit the fifth period in the D blocks, it can get very messy. But this is good practice to try a couple of these and make sure you can end up with the ground state species. But one of the last things that's really important to note is that because a lot of these electron configurations only depend on the number of electrons, we tend to see our periodic trends definitely emerge. And it's important to think about the fact our periodic trends, the reason why they derive based on the number of electrons is because it's also partially where those electrons land. So what is the correct term symbol or configuration? And they tend to be fairly constant as you walk through the periodic table. So that ends up bringing us to the end of Hund's rules and how to predict the lowest energy species. Next time, we're going to bring everything we've done so far together and revisit electron excitations, now with a dash of term symbols. So take care, stay healthy, let me know if you need anything.